Take a language model, a GPT, a llama, whatever you like, and train it on increasing amounts of text. As you feed it more data, its loss goes down. Simple enough. If you break that loss into pieces, separating out how well the model predicts using one word of context, 2, 4, 8, you get this tangle of curves. Each context length follows its own path. There's no obvious pattern connecting them. Now watch what happens when we rescale the axes. Every single curve collapses onto one. Same data, different coordinates, perfect alignment. This is a prediction made by a theory that derives neural scaling laws entirely from two statistical properties of language you can measure without training any model. No free parameters, no curve fitting, just the structure of language itself. In this video, we'll understand where that collapse comes from and why the rate at which language models improve with data is determined not by the model architecture but by properties of the language it's learning. Before we get to the theory, we need to understand scaling laws. When you train a language model, its loss improves with more training data. Plot loss against dataset size, and you get a curve that drops steeply at first, then levels off. Familiar shape, but hard to work with. Plot the same data on a log-log scale, and something happens. The curve becomes a straight line. This is a power law, loss proportional to p to the negative alpha. That exponent alpha matters enormously. It tells you exactly how much you gain from doubling your data. AI companies use these exponents to plan training runs that cost millions of dollars. Data scaling laws were first documented by Kaplan and colleagues and refined in the Chinchilla paper in 2022. But the exponents were always measured and not predicted. There's no theory explaining them. And here's the puzzle. Different datasets give different exponents. Train on tiny stories, which is a dataset of simple children's stories, and you get 1 alpha. Train on Wikitext, which is made up primarily of Wikipedia articles, and you get a different alpha. The exponent clearly depends on the data. But on what property? What is it about a text corpus that determines how fast a model can learn from it? To understand scaling laws, we need to look more carefully at what a language model is learning. A language model predicts the next token given all the tokens before it. If the text reads, "the cat sat on the model assigns a probability to every possible next token. The loss measures how surprised it is by the actual next token, averaged over the training set. We can break this down by how much context the model uses. The 1 gram loss measures prediction with no context, just overall token frequencies. The 2 gram loss uses 1 previous token. The 3 gram loss, 2 tokens, and so on. Each additional token of context helps, so these losses form a decreasing sequence. Every n gram loss has a floor, the conditional entropy, the irreducible uncertainty about the next token given n tokens of context. The language itself has randomness that no model can eliminate. The conditional entropy is a property of the language, not the model. And here's the first key finding. As you increase the context length n, the conditional entropy decreases as a power law. The gap between the conditional entropy and its infinite context limit scales as n to the negative gamma. For tiny stories, gamma is about 0.34. For Wikitext, it's about 0.27. This gamma is one of the first of 2 statistical fingerprints we'll need. It captures how quickly additional context reduces uncertainty, and it's consistent across different model architectures. The second fingerprint is about correlations between tokens. Consider 2 positions in a text separated by n tokens. They're not independent. If you see ocean at one position, words like waves or shore become more likely a few tokens later. But this statistical relationship weakens with distance. 5 tokens apart, strongly correlated. 50 tokens apart, much less. 5,000, barely at all. We can quantify this by measuring the token-token covariance at each distance n. The strength of these correlations decays with n as a power law, with exponent beta. For tiny stories, beta is about 0.88, whereas for Wikitext, it's about 0.94. This is the second fingerprint, how quickly statistical relationships between tokens fade with distance. Like gamma, it's a property of language, not the model. We now have 2 numbers that describe the statistical structure of a text corpus. What the paper shows next is how these 2 numbers, and only these 2 numbers, determine the scaling law exponent. The link between gamma, beta, and the scaling law is a concept the paper calls the prediction time horizon. A model trained on p tokens can only effectively exploit context up to some distance n times p in the past. Tokens further back carry useful correlations, but the model hasn't seen enough data to detect them. Why not? It's a signal-to-noise problem. The correlation at distance n has strength roughly n to the negative beta, but estimating it from a finite dataset introduces sampling noise on the order of 1 over root p. The model can only detect correlations whose signal exceeds the noise. Setting them equal and solving for n gives us the prediction time horizon. N times p is proportional to p to the power of 1 over 2 beta. More data means a longer horizon. With little data, the model is limited to very local context. As data grows, longer range correlations emerge from the noise. Each extension of the horizon unlocks a new layer of context, and each layer reduces the loss by an amount governed by gamma. More data extends the prediction horizon. Each extension reduces loss at a rate set by the entropy structure of the language. We can now derive the scaling exponent. The autoregressive loss decomposes into two parts: a boundary term, the conditional entropy at the prediction time horizon, h at n times p, and excess losses from imperfect use of context within the horizon. The paper identifies a regime called fast learning within the horizon, where models quickly learn to use all context within their reach. In this regime, which the data supports, the boundary term dominates. The chain L minus h infinity is approximately h at n times p minus h infinity. From the entropy power law, this equals n times p to the negative gamma. From the prediction time horizon, n times p equals p to the 1 over 2 beta. Substituting, L minus h infinity is proportional to p to the negative gamma over 2 beta, and there it is. The data-limited scaling exponent is alpha sub d equals gamma over 2 beta. No free parameters, no fitted constants, just two measurable properties of the language. Let's check it. Tiny stories, 0.34 divided by 2 times 0.88 gives about 0.19. Wikitext, 0.27 divided by 2 times 0.94 gives about 0.14. Both match the experimentally measured scaling exponents. This theory makes an even stronger prediction than just the overall exponent. It predicts that all the individual n-gram learning curves should collapse onto a single master curve when the axes are rescaled. Here's the logic. Each n-gram loss L sub n has its own natural data scale. The data threshold P sub n at which the model first has enough data to detect correlations at lag n. From our theory, this threshold scales as n to the 2 beta, and at each has its own natural loss scale, the conditional entropy h sub n, which scales as n to the negative gamma. If we rescale the x-axis by dividing p by n to the 2 beta, and rescale the y-axis by multiplying L sub n by n to the gamma, all the curves should collapse onto a single curve. And they do. The rainbow of separate trajectories we saw at the start of the video falls onto a single line. This isn't a fit. The rescaling uses only gamma and beta, measured independently from the entropy decay and the correlation decay. The collapse is a genuine parameter-free prediction, and the fact that it works across context lengths spanning 2 orders of magnitude is powerful evidence that the framework captures real mechanism of data-limited learning. This result reframes how we think about scaling laws. The exponent isn't a property of the model, it's a property of the data. The same exponent emerges whether you train a GPT-2 with absolute position embeddings, with rotary embeddings, or a llama. The architecture affects the prefactor, but the slope is set by the language. The paper draws an analogy to universality classes in physics. Near phase transitions, very different physical systems, such as magnets, fluids, lattice models, share the same critical exponents. What matters is the symmetry and dimensionality, not the microscopic details. Same idea here. Different architectures, same exponent, because what matters is the statistical structure of the data. Open questions certainly remain. Does this extend to the trillion token scale? Does fast learning within the horizon hold within the context windows of 100,000 tokens? But as a first principles theory linking scaling laws to measurable properties of language, with no free parameters and no synthetic data, this is a striking result. The shape of neural scaling laws is written into the statistics of language itself.